Okay, so here we are with section 5.2. I guess this is part 5. We're finding area still. So we're finding the area bounded by that curve. F of x equals, what is that? Negative x cubed plus 6x. The x-axis, x equals 0 and x equals 2. This is what it would look like. Now, one thing to keep in mind is clearly this function is not always positive. There are sections where it is negative. But on the interval that we care about, that is from 0 to 2, we are looking at a non-negative function, ranging from 0 to a high of, what is that, like 5.5 or so. My job is to find that green shaded area. As I've said before, geometry has failed us because that is not a geometric shape. So I need to use calculus. So I am going to set this problem up. So let's set this up. Let's see. All right. So according to Reimann Sums, the area is going to be the limit as the number of rectangles n approaches infinity of the summation as I goes from 1 to n of the function at a sample point, f of c sub I, times the delta x, the width of the intervals. So let's go ahead and figure out some of these pieces in here. Specifically, let's figure out what we're going to use for c sub I, and let's figure out what we're going to use for delta x to make this thing work. All right, so c sub I, because I'm lazy, I'm going to use rights, and rights are defined as a plus I times delta x. So before I can go ahead and figure that out, I need to know what delta x is. So delta x, by definition, is always b, the right endpoint of the interval that we care about, minus a, the left endpoint, divided by the number of rectangles. In this case, that's going to be the variable that's going to go off to infinity over there. So specifically, we're looking at 2 minus 0 divided by n, or just 2 over n. And now that I know that 2 over n, I can use it up there. Okay? So I'm going to go back and say then that c sub I, our sample point, we're going to use right endpoints, is going to be a, which is 0. Remember, a is the left endpoint, plus I times 2 over n. Or if you prefer, clean that up a little bit, that's going to give me 2i over n. Okay? And so now what I'm going to do is I'm going to take all of this, plug it in there, and then grind out the answer. So my area is going to be equal to the limit as n approaches infinity of the summation as I goes from 1 to n of f of 2i over n times delta x, which is 2 over n. So next step, I need to evaluate this. Okay? So I'm going to use the function f of x, but replace all the x's with our c sub I, our 2i over n. So now I've got the limit as n approaches infinity of the summation as I goes from 1 to n of 2i over n cubed, but make it negative, plus 6 times 2i over n, and then this whole thing is going to get multiplied by 2 over n. Okay, now this next step, I'm going to do a whole bunch in one step, but I'm going to apply all these limit rules. So I'm going to apply a limit rule because of this multiplication. I'm going to apply a limit rule because of this addition, and I'm going to make this thing be a lot simpler. Okay, so then that's going to give me the limit as n approaches infinity of, a great big set of parentheses here because I'm going to have 2 over n times the summation of negative 8i over n plus the summation of 12i over n. Let's see, I need this here too, because that 2 over n needs to get multiplied by both summations. Now you notice something that I did, and it's a somewhat acceptable laziness. Do you notice that I left those off when I did my summations and I just wrote the summation? It's not precise and some people might get upset about it, but it's a nice simplification because it cleans things up a little bit. Okay, I just also realized that there's a mistake there too. This should be I cubed over n cubed, but that's okay, all right? So now what I need to do is I need to apply some formulas to I cubed and I in those summations. All right, so let's apply those formulas then. So I'm going to change the purple. And so now I'm going to have that the area is equal to the limit as n approaches infinity of 2 over n times negative 8 over n cubed times, and now I'm going to do the summation rule for I cubed. I cubed is going to be n squared times n plus 1 squared over 4. And then plus 2 over n times 12 over n times the summation formula for plain old I. That's going to be n times n plus 1 over 2. And so now what I want to do is I want to find out what these are all equal to, because I got to take the limit at infinity. Now, as in the last problem, what I want to do is I want to apply, and I'm just going to zoom in on this. I want to apply some of those tricks that I learned back in college algebra about horizontal asymptotes, because that's what's going to happen here. Now, I'm just going to look at this first one for right now. Okay. First thing I'm going to do is I'm going to do a little bit of algebraic cleanup. Let's see. The coefficients in the numerator are the 2 and the negative 8, which gives me negative 16. The coefficient in the denominator is a 4. So if I cancel, I'm just going to get a negative 4 upstairs. Okay. Now, I don't want to multiply this out, but do you see how if I did, the leading term would be n to the 4th plus a whole bunch of other stuff? And so my numerator is going to be negative 4 n to the 4th. My denominator is just going to be n to the 4th. So then the horizontal asymptote, since they both have the same highest power, they're polynomials at n to the 4th, my horizontal asymptote will just be the ratio of the coefficients, or negative 4 divided by 1, or negative 4. Now I'll move to the second one over here. I got to do this one now. I'm going to use the exact same logic. Okay? Again, I don't want to multiply everything out, but you see how this 2 will cancel this 2, and I'm going to get a 12 upstairs as my coefficient. If I multiply this out, I'm going to get, well, I can multiply this one out because it's so easy. N squared plus n. Downstairs, I just have n squared. Polynomial over polynomial, horizontal asymptote is the limit at infinity. So I've got 12n squared over n squared, so the ratio of the coefficients is 12, and 12 plus negative 4 is 8. So that means that the area is 8 square units, whatever those units would be. So what does area mean? Well, it all depends on what your units are. And what I mean by that is, suppose that this was, say, I don't know, hours, and this was miles per hour, and you found area. Well, when you find that area, you're multiplying horizontal units by vertical units. So what are miles per hour multiplied by hours going to give you? Well, hours are going to cancel, and we just get miles coming out of that. Right? So then if this was measuring miles per hour in hours, we would say that this area means we went 8 miles, or we traveled 8 miles. All right, let's try another problem. Find the area bounded by this parabola, x squared plus 2x, the x-axis, x equals 0 and x equals 3. All right, so let's go ahead and take a look at the graph. All right, so first off, like I always want to do, I want to see what the picture looks like. So over here I have it graphed. There's our function on the interval 0 to 3. From x goes from 0 to 3. It looks like we're non-negative, so I can find the area using this Reimann approach. So let's make this happen. Okay. So the area is going to be equal to the limit as the number of rectangles n approaches infinity of the summation as I goes from 1 to n of f of c sub I, our sample point, times our delta x. And just like last time, just like next time, just like every other time I've done this, the first thing I need to do is figure out what delta x and c sub I are. Now the formula for delta x says it's always b minus a divided by n. So 3 minus 0 divided by n, or 3 over n. Our c sub I, our sample point, because I'm lazy, I'm going to use the right endpoint. Right endpoint is always a plus I times delta x. In this specific example, a is 0, plus I times 3 over n. Wow, that got ugly real quick. Can't scribble on top of it. 3 over n, or if you prefer, 3i over n. And so now what do? Oh, I take this, put it there, I take this, put it there, and I grind out all the mathematics. What a fun time this is going to be. All right, so here we go. Area is equal to the limit as n approaches infinity of the summation as I equals 1 to n of f of 3i over n multiplied by 3 over n. Now I have had a couple students get confused because they think that this is missing an I. So be careful. Remember that that is delta x right there. That's the delta x. It doesn't have the I in it. Oftentimes, very common for delta x and your c sub I, your sample point, to look really similar. And it's because delta x lives inside of c sub I. If you look at what's going on there, when you calculate c sub I, there's a delta x in it. So it's very common for those to look similar. So make sure when you're looking at these, you're seeing them for what they are. This is delta x. This is c sub I. Okay, so our delta x and our c sub I. Next step, I need to apply the function f of x here and see what happens. So let's see that I'm going to get my area is going to be equal to the limit as n approaches infinity of the summation as I goes from 1 to n of, and I'm going to move this 3 over n out into the front here. 3 over n times f of 3i over n. So that's going to give me 3i over n squared plus 2 times 3i over n. Okay. Now it's time to do a whole bunch of algebra. So I've got the limit as n approaches infinity of the summation as I goes from 1 to n of, let's see, 27i squared over n squared plus n cubed, sorry, down there. 3 times 2 times 3. Well, 3 times 3 is 9 times 2 is 18 I over n squared. Okay, if you're wondering where the 27 came from, 3i squared is going to be 9i squared times another 3 from out in front there, 27. And then I'm going to have an n squared there times another n to give me my n cubed. And the same thing when I distribute that 3 over n into that second term, I got the 3 times the 2 times the 3, so that's 6 times 3, 18i over n times n squared. Okay. Now at this point, I'm going to apply summation formulas. And so I'm going to have the limit as n approaches infinity still, but summation is going to go away. In the first one, I'm going to have 27 over n cubed times the rule for I squared, and the rule for I squared is n squared. Oh, no, I'm sorry, n times n plus 1 times 2n plus 1 all divided by, I believe, 6. Yeah. Plus, that looks good. I'm going to have an 18 over n squared for the second one times the summation rule for I, which is n times n plus 1 divided by 2. And I want to take the limit as n approaches infinity of that whole hot mess. Okay? I'm going to do them separately. I'll look at this one first, and then I'll look at this one. Okay? So looking at the first one, I get, let's see, if I multiplied that out, and I don't want to multiply out, but if I multiplied that numerator out right here, and let me zoom in on it, I would get a 2n cubed plus a bunch of junk. Okay? So then my numerator is going to be that 27 times that 2n cubed plus a bunch of junk, and the denominator is going to be 6n cubed. So then the limit would be the ratio of those coefficients. So it would be 27 times 2, which is 54, divided by 6, plus the second term. Well, if I multiply this out, I'm going to get an 18n squared upstairs and a 2n squared downstairs. And of course, this is plus another, what is that going to be, 18n? Horizontal asymptote, ratio of the coefficients, 18 divided by 2. I'm just going to do that. That's 9. Okay, and I'm just looking back here at this and realizing that that 4 doesn't look enough like a 4. The 54 divided by 6 is 9, and so then I get that the area, 9 plus 9, 18 units squared, whatever that is, 18 square units. Okay? All right, so I'm finding area. I'm using Riemann summations. I am taking the limit as the number of rectangles n approaches infinity. I set up the summation. First step, solve for or find, however you want to word that, your delta x and your sample point c sub I. Now, I've used right endpoints, but there's no reason why you couldn't use lefts or midpoints or anything else. The only argument that I make for using rights all the time is it's the cleanest formula. It's the easiest formula. Okay. Once I find those, then I start plugging things in. So here, I'm just simply plugging in what c sub I and delta x mean. Here, I'm replacing f with the actual algebra of x squared plus 2x. Here, I'm just multiplying and cleaning things up algebraically. From here to here, you'll notice the summations have gone away. The summation's gone away when I use those formulas from earlier in the section, the summation properties way up at the top of the page. Okay. And then after that, it's just simply doing some arithmetic. 54 divided by 6 is 9. 9 plus 9 is 18. And there we go. We've got a lovely 17-minute video for the last two problems. All right. Have a great day, and I guess I'll see you back here for section 5.3.